This mini lecture is about competition between substitution and elimination reactions. Now we've already talked about the substitution pattern. This occurs when the y minus comes in and replaces the x, and we end up with the y being where the x was and the x coming off as x minus. But there is another reaction that can occur when y minus reacts with this compound, and that's called elimination. Now instead of the y minus coming in and attacking this C and replacing the X group, what it does is it takes off a hydrogen on the C that's next to the C with the X group. Now when it does this, it forms a double bond compound. This is called elimination. YH forms, which is the conjugate acid of the base that is attacking, and we get the double bond compound, and then X minus is also formed. So there's two ways that this elimination mechanism can occur. It can occur via an E1 mechanism, and this is similar to the SN1, where the X minus group comes off first, leaving a carbocation, and then Y minus comes in and takes off the hydrogen on the C next to the C plus. This leaves a compound with a double bond. The other possibility is an E2 mechanism, where the Y minus comes in, takes the H, and then simultaneously the electrons from the H come in and form the double bond, and then simultaneously the electrons go to the X and the X comes off as X minus. This also forms a double bond compound as well. Right, before we figure out what conditions are going to favour substitution and which ones will favour elimination, we need a little bit of groundwork. We need to first of all define what I mean by a strong nucleophile and what I mean by a strong base. A strong nucleophile includes things that have S negatives, things that have N3 negatives and Cn negatives, and all of these will favor substitution reactions. What we know about substitution is that it's favored by strong nucleophiles. Now I'll explain over here what I mean by a strong nucleophile. Strong nucleophiles can elongate their negative charge, and if they can elongate, they can more easily attack a C with a halogen or some sort of leaving group on it. So those kinds of compounds will end up being favored for substitution. On the other hand, compounds that have O negatives tend to be strong bases. Strong bases have a greater attraction for hydrogen than they do for attacking Cs that have halogens attached or leaving groups. That's because due to their electronegativity, the O negative will keep its charge close in to the O negative, which means it doesn't really want to elongate and attach to Cs very much. So what it will do instead is take an exposed hydrogen, and if it can take an exposed hydrogen, that will lead to a double bond compound. All in all though, you can look at this and you can say, well, anything with an O negative is going to be a strong base. Anything with an O negative will therefore favour elimination. All the other nucleophiles we'll deal with, I guess you can consider those to be strong nucleophiles. The other factor that's important is that heat will favour elimination as well, and room temperature will favour substitution. The reason for this probably has a lot to do with the activation energy required to get elimination and substitution to occur. So we can take a look at that. Alright, so we've got our energy profile here. So we've got energy, we've got reaction pathway. This might be a typical SN2 energy pathway, and this might be a typical E2 energy pathway. As you can see, the activation energy required to get the E2 is going to be greater than the activation energy required to get the SN2. Thus, at high temperature, it's possible that E2 could be favoured. Even though there's enough energy to get to the SN2, it's also possible that the E2 might lead to products that are more stable than the SN2 products. So that may end up favouring elimination. Overall, though, we find that high temperatures tend to favour the elimination process. So in summary, what we can say is if we have room temperature and a strong nucleophile, we're going to favour substitution. Strong base and heat will favour elimination, and strong nucleophile and heat and strong base and room temperature will favour both substitution and elimination products. This kind of table, you'll get some sort of version of that with your test. That's not something you have to memorize. Alright, so here's some examples. SH negative and room temperature. So SH negative doesn't contain an oxygen, so we're going to call that a strong nucleophile. Room temperature, so we're thinking about just substitution as being room temperature, strong nucleophile, just a substitution product. So all we're going to see is the Br being replaced with the SH. Now you need to be a little bit careful with this. Let's say we've got something like this and we're reacting with SH minus and it's room temperature. So what we want to do is we want to replace the Br with the SH. And that would be the substitution product. Understand also that we would get Br negative as a side product, but I'm not really too interested in the side products. I'm only really interested in the product that we're getting from the carbon chain. Now be careful and make sure that you don't do something like this. Make it SH and then keep the negative charge on the SH, because that is not within the substitution pattern. What happens is the SH negative attacks and transfers its negative charge to the bromine, so the bromine becomes a bromide ion. This compound that we form here is neutral and always will be neutral. Alright, so this one gives a single product, just a substitution product. Here's an example where we've got OMe minus, that's going to be a strong base because it's got the oxygen in it, and heat, so we're looking at just elimination. So we're going to get elimination products out of this. Now what's going to happen, and I'll draw a picture of this. Is we've got the Br, and instead of OMe minus coming in and replacing the Br as a substitution, what it's going to do is remove a proton either here or here. Now notice it's the H connected to the C that's next to the C with the Br, and that's the way it always is in elimination. So what's happening is it's going in, taking that H, and then that's forming the double bond, and then the Br is leaving. Thus, what we can say is, as a general rule and a general pattern, this works out very well for elimination processes, is that we can just get rid of the Br and draw a double bond either here or here. So the Br is gone and we're just left with the double bond either this side or this side. It turns out though, if you look at both of these, they're actually exactly the same. So we only get one product out of this elimination process. and that's this one here. Now, as you might expect, let's say we have a strong base in room temperature. The strong base will favour elimination, the room temperature will favour substitution. What this leads to then is a mixture of two products. One for substitution, where the Br gets replaced with the OMe. Now again, remember the negative charge is no longer on the OMe, it got transferred to the Br when the Br left. And we can get the elimination product as well. So this process will lead to two products, one elimination product and one substitution product. And we don't know how much of each we're getting, all we know is we're getting some of each of those. Right, the other thing we have to consider is when we get more than one alkene product, and occasionally we will, what that's going to lead to is a possibility of having a main elimination product and a minor elimination product. We can decide as to which product will be the main product by looking at the overall stability of the double bond that we're getting. And it turns out that the more carbons we have attached to double bonds, the more stable those double bonds will be. It's called the Zaitsev rule. So looking at this one, and I'll draw this on the page. Now, if we were just looking at this and we were doing the OMe minus and we were just using heat, then again we would only expect elimination products to form from this one. Now when the elimination product forms, we can take off the Br, and I'll show that over here. We can take off the Br and we can draw a double bond out to any carbon that actually has a hydrogen attached to it. So this one would have a hydrogen here, this one would have a hydrogen here, and these are the hydrogens that end up getting removed. Now if there's no hydrogen attached, and there's no hydrogen attached to this C, then we can't form a double bond out here. That would lead to a carbon with 5 bonds on it, so we can't do that. But we can form these two products. This one and this one. I'll just draw the other one that doesn't occur so that you can be convinced why it doesn't occur. And that would be because you see you end up with 5 bonds on that carbon, so there's no way that we can ever get a product that looks like that. And because of the mechanism basically states that you have to take off a hydrogen from the C that's next to the C with the bromine. If there's no hydrogen there to take off, then we can't get a double bond here. There are hydrogens here and here that can be removed, so we get 2 products, this one and this one. It turns out though one of these is the main product, and what we do is we can count the C's directly connected to the double bond, and that will give us an idea of its stability. Now since this one has 3 C's connected and this one has 2 C's connected, we're talking about direct connection to the C's that make up the double bond, then we can know this one would be the main elimination product. Now this only tells us about elimination products. It gives us no information about substitution products, but if you've got more than one elimination product, this will allow you to tell which one is the main one. So finally, just one more example. This one, you've got OH minus, which is a strong base. That's going to favour elimination. You've got room temperature. That's going to favour substitution. That's going to give you 3 possible elimination products. Now each one is explained by removing the Br and then drawing a double bond out here, double bond out here, and a double bond down here. There's your 3 elimination products. We can also get a substitution product, which is just found by doing a straight substitution of the OH for the Br. Remember, there's no negative on the OH anymore. Now out of these 3 we can figure out what the main alkene is going to be, and that will be the one that has the most C's connected to the C's that make up the CC double bond. Now if you look at this CC double bond, it's got 1, 2, 3, 4 C's directly attached to the double bond. This particular one has 1, 2 carbons directly attached to the C that makes up the double bond, and this one has 1, 2, 3 carbons. Since this one has the most, then it's going to be the main alkene, or the one that's most prevalent.